So first thing we want is a picture, and the parabolas that they're giving us here, you guys can graph these. You should know what these look like. 16 minus x squared starts up here and comes down. All right, and y equals x squared starts here at the origin and goes up. Okay? And what I'm asking you to do is tell me what's the largest rectangle that I can inscribe in there. And remember, inscribe just means that the vertices are just sitting on that curve, so it's going to look something like this. Okay? So you can imagine we can put multiple different rectangles. We can put a really like thin, tall one. We can put a really flat, thin one, or we can put one that's almost like squarish in here. Okay? So remember we said, and anytime you're working with the coordinate axis, the Cartesian whatever coordinate system, you should switch everything to x and y. But first we're just going to start with the formula for what we're trying to maximize. In this case, we want to find the largest rectangle. So when they say largest rectangle, what do they want us to maximize? Area. Yeah, we want the area of this rectangle to be as large as possible. So the area of the rectangle is length times width. Cool. But we want to switch that to x's and y's. So remember we said that, yeah, this point up here is really just x, y1 if you think about it. Now the problem is, when we did this before, the bottom side was always on the x-axis, and that's not happening now. Now it's determined by another curve, which is x squared. So now we need to know that the coordinates of this point down here are really x. They have the same x value, but they're going to have a different y value. Okay, so I'll call it y1, y2. Cool? So the length of this thing is going to be 2x, because x is this distance from here to here. So when you go to the other side, the full length of that rectangle is going to be 2x, but the width is not going to be just y. Okay, because we have two y's now. How do we tell the distance between them, which is what we really need? Yeah, you subtract them, okay? So what's that? It's going to be y1 minus y2 in this case. Just because of the way that I've labeled them, I put y1 on top. That's how wide that rectangle is. Okay? Now we don't want x's and y's in here because we're going to derive it, which is unlike related rates, like you can derive with respect to time. Here we need to derive with respect to one of our variables. And this happened before too, we know that the y's are really just formulas for x's. So y1 is 16 minus x squared. Oops. And y2 is just x squared. Cool? So now we have a formula for the area of this rectangle, just in terms of x, and we simplify it and we derive it. So this is going to be 32x minus 4x cubed. Okay? So we got 32x minus 2x squared, that's right, 4x cubed. Okay, so we derive this, and we find the critical numbers. So dA dx is going to be 32 minus 12x squared. And we need to know where that's 0. So it turns out that's going to happen when 32 equals 12x squared, which means x squared equals 32 over 12. But 32 over 12 reduces down to what? 8 over 3? Then we'll take the square root of that. So x, which I'll write on this side, is going to be plus or minus the square root of 8/3. Okay? And since just the way that I've defined my picture, I'm putting x on the positive side of the y-axis. We know that the critical number is root 8 over 3. Okay? So we are going to make our number line just to verify that that's really a maximum. So the smallest x can be is 0. What's the largest x can be from this picture? What point represents the largest x can be? Where they intersect each other, okay? And that happens to be at the square root of 8. Okay, so that x value right there is the square root of 8. So that's the largest that x can be in this particular example. And the square root of 8/3, somewhere like right here. Okay? Not crazy important because, I mean, you know hopefully what this derivative looks like. That's a parabola opening downward, right? Negative 32x or 12x squared. So if you plug in a small x value, like 0.000001, then the derivative is going to be positive because you get 32 minus a small value. So that means it's positive on this interval. If you plug in a big x value, I don't know, like 2, then you're going to get 32 minus 48, which is negative. Okay? Which means that root 8 thirds is the x value that maximizes this rectangle. And what was the question? Find the dimensions. So the dimensions are going to be, the length of it is going to be 2 root 8 thirds, so we should really simplify down this. So the square root of 8 thirds is the same thing as 2 square roots of 8 over square roots of 3. Cool. And 8 is the same thing as 2 root 2. So this is really 4 root 2 over root 3 is the length. And if you wanted to rationalize it, you could. Then it's really 4 root 6 over 3. And then the width, remember we had a formula for the width. It was right here. It was 16 minus 2x squared. Okay? So if we do that, this was the width. This is what we said the width had to be. But we know that x was root 8 thirds. So this is really 16 minus 2 times root 8 thirds squared, which is really 16 minus 16 thirds, which is really 48 thirds, minus 16 thirds, which is really 32 thirds. Cool. So the length is 4 root 6 over 3, and the width is 16 thirds. And there's no units on that, but those are the dimensions of the rectangle that has the largest area.